Before we can learn how to navigate over the Earth's surface, we need to understand how it evolved into the familiar spherical blue planet. This lesson will describe the form and shape of the Earth, and how the Earth is spinning in orbit around the Sun. The Earth evolved from gas billions of years ago. A swirling ball of this gas then cooled and solidified to form the planet. As the gas solidified, the centrifugal force created by the spinning produced slightly more mass around the middle, and it became a distorted sphere. The Earth, therefore, is not perfectly spherical. It is slightly distorted, being more wide than it is high. This difference in diameter is called the Earth compression. The compression of the Earth is described in terms of its height, the polar diameter, against its width, the equatorial diameter. The polar diameter is some 27 statute miles less than the equatorial diameter. This equates to 23 nautical miles, or 43 kilometers. The difference between the equatorial and polar diameter can also be expressed as a percentage of the equatorial diameter, and this is 0.3%. Or as a fraction, it is 1/300th. The Earth's shape is referred to as an oblate spheroid. The Greek word for Earth-shaped is geoid, and this is sometimes used to describe the shape. There is a slightly larger amount of mass in the southern hemisphere, although this is insignificant in navigation terms. This lesson will give you an understanding of direction and the conventions we use in determining direction. Before we can define direction on the Earth, we need to select a datum from which direction can be measured. As we have seen, the Earth spins on its polar axis. We say that the direction in which the Earth is spinning is called east. All other directions are defined in relation to east. West is defined as the opposite direction to east. We can also use the poles to define direction. When we are facing east, the pole to our left is called the North Pole, and the direction to it is north. The pole on our right when facing east is called the South Pole, and the direction to it is south. To successfully navigate an aircraft, we need to accurately refer to positions on the surface of the Earth. The aim of this lesson is to describe latitude as used in the position reference system. Firstly, we will see how position is defined on a flat or plane surface. The route depicted here can be represented on a flat piece of paper, for example a map, going from the start point to the end point. The start point or departure point we will call A, and the end point or destination we will call B. Let us look at how to define the position of point A using the x and y axes. We can say that the position of A is defined by the value along the x-axis, 1, and the value along the y-axis, 3, and that position B can likewise be defined by the value along the x-axis, 5, and the value along the y-axis, 1. Determining positions on a flat plane in this manner is referred to as using the Cartesian coordinate system. To transfer these coordinates onto the spherical shape of the Earth, we use a similar method to the Cartesian coordinate system that we have just seen, but need to modify the x and y axes used on a flat piece of paper. The position reference system used on the Earth refers to coordinates using the terms latitude and longitude, which replace the linear x and y axes with a system of angular measurement. Latitude and longitude define a position on the surface of the Earth using angular measurement in degrees and minutes, for extremely accurate and unambiguous position reference. Longitude is the other coordinate that, with latitude, defines a specific position on the surface of the Earth. Like latitude, longitude is an angular measurement, measured at the centre of the Earth. However, unlike latitude, the equator cannot be used as the datum to measure the angle. What is needed is another datum that is at 90 degrees to the equator. Lines that run from pole to pole and cross the equator at 90 degrees are called meridians. There are many meridians on the Earth, but we need to identify one of them as a reference. The particular meridian used as a reference is called the prime meridian. It is this meridian that longitude is measured from. The prime meridian runs from pole to pole and bisects a place in London called Greenwich. The prime meridian is often referred to as the Greenwich meridian for this reason. Longitude of any point is the shorter angular distance of the arc along the equator, between the prime meridian and the meridian through that point. The angle is measured in terms of whether it is east or west of the prime meridian. In this example on the screen, the longitude is west of the prime meridian. If the angle at the centre of the Earth between these two meridians was, for example, 40 degrees, then the longitude would be west 04000. This means that the longitude is 40 degrees 0 minutes west of the prime meridian. All longitudes are 5 figures. The first 3 are degrees, and the last 2 are minutes. Longitude can be a maximum of either west 18000 or east 18000. This meridian is on the opposite side of the Earth to the prime meridian. A meridian that is 180 degrees from another meridian is called an antimeridian. In the case of the Greenwich meridian, the east or west 18000 meridian is the antimeridian of the Greenwich meridian. We have seen that latitude is measured in degrees, either north or south of the equator. We will now look at what happens when we move from one position to another, in terms of the change in the latitude. Chelat is an abbreviation for a change of latitude, from one latitude to another latitude. If we were to move from the equator, north-south 0000, to north 3000, we would have travelled through 30 degrees of latitude. In other words, the chelat would be 30 degrees. In this case, the direction would be north. Let's look at some special lines of latitude and the chelat when moving from one to another. There are several special lines of latitude on the Earth. These are the Arctic Circle, the Tropic of Cancer, the Equator, the Tropic of Capricorn, and the Antarctic Circle. We can determine the chelat from one to another. For example, from the equator to the Tropic of Capricorn, we can see that the chelat is 23.5 degrees in a southerly direction. From the Tropic of Capricorn to the Antarctic Circle, the chelat is another 43 degrees, still heading south. If we went from the Tropic of Capricorn to the Arctic Circle, we would have 23.5 degrees to go to the equator, and then a further 66.5 degrees to go to the Arctic Circle. The chelat would therefore be a total of 90 degrees in a northerly direction. When moving from one longitude to another, the change of longitude is referred to as Qilong. To consider a calculation of Qilong, it is best to view the Earth looking down onto one of the poles. From the Greenwich meridian to 30 degrees west, west 03000, an angle of 30 degrees is subtended at the centre, as seen in the diagram. Now consider the meridian east 100 degrees, east 10000. What is the Qilong from this meridian to the 30 west meridian? Looking at the diagram, we can see that Qilong must be 30 degrees plus 100 degrees. 130 degrees is the answer. Now let's consider another example to 170 east, east 17000, from the 30 west meridian. It is now apparent that there are two angles between the two meridians, one of 200 degrees and one of 160 degrees. However, it is usual to only consider the smaller angle, as this would represent the shorter distance between the two meridians. The correct Qilong is therefore 160 degrees. Likewise, determining the Qilong from west 17000 to east 17000, the smaller angle in this case would be 20 degrees. This lesson looks at properties of lines that can be portrayed on the surface of the Earth. The first of these lines is prescribed by the notion of a great circle. A great circle is a circle on the surface of the Earth whose centre and radius are those of the Earth itself. It is called great as the disk cut through the Earth is always of the greatest possible area. The circumference of a great circle forms the path to be followed on the Earth's surface for flying a great circle track. Now, let's imagine an orange, a perfectly spherical orange. Take a length of string and pull it tightly just above the surface. As the string cannot be pulled any tighter or made shorter, it will find the shortest distance between 2 points on the orange. The string actually follows the lines prescribed by a great circle. It can be seen on the screen that the green line is shorter than the red line. The shorter arc of the great circle is therefore the shortest distance between 2 points. There are many occasions in navigation when we fly a great circle path to follow the shortest path between 2 points. Given 2 points on the surface of the Earth, there will only be one great circle joining them, unless the 2 points are exactly diametrically opposed. In addition to great circles, we also have small circles. There are also lines on the Earth's surface prescribed by circles. A small circle differs from a great circle as it does not have the same centre or radius as that of the Earth. Small circles can run in any direction over the surface of the Earth, provided that the centre and radius does not coincide with that of the Earth. Good examples of small circles are parallels of latitude. All parallels of latitude are small circles, except for the equator. The equator has the same centre and radius as that of the Earth, and is therefore the only parallel of latitude that is actually a great circle. Small circles do not necessarily have to run east or west, as in the case of parallels of latitude. Small circles can run in any direction, as long as they do not have the same centre or radius as that of the Earth. Vertices are a phenomenon relating to great circles. By definition, a great circle has the same centre and radius as the Earth itself. The vertices of a great circle at the northernmost and southernmost position of the great circle. The vertices are antipodal, in other words, diametrically opposite. From the example on the screen, the northern vertex of the great circle is 63 degrees north and 10 degrees east. The southern vertex will have the same value of latitude, except it is south, in this case 63 degrees south. The great circle will have these two antipodal points on a meridian and its antimeridian. In this example, the northern vertex is on the 10 east longitude meridian, and the southern vertex is on the 170 degrees west longitude antimeridian. The sum of the two longitudes will always equal 180 degrees, indicating a meridian and its associated antimeridian. Vertices have some interesting properties. The great circle will cross the equator at the 2 points whose longitude is 90 degrees from either vertex, in this case 100 east and 80 west. The great circle will cross the equator at an angle equal to the latitude of its vertex. In this case, the angle is 63 degrees. The direction of the great circle can be determined from this crossing angle. At either vertex of the great circle, the track direction is either 090 or 270 degrees. All meridians converge to a point at either pole. Depending on the proximity of a track to the pole and the relative angle, track direction can change quite rapidly. Sometimes it is useful for ease of navigation to follow a track that does not change direction. Constant changes in track nowadays do not pose a significant problem, as technical advances in navigation equipment can easily cope with constant track changes. A line that does have constant direction is called a rhumb line, and this line will cut each meridian at the same angle. A rhumb line therefore has the advantage of a constant track. From the diagram on the screen, we can see that a typical great circle track follows a different path over the Earth's surface to the rhumb line track, between the same departure and destination positions. Understanding distance measurement is a fundamental aspect of navigation. In this lesson, we will look at distance definitions and conversion between imperial and metric systems that are used to measure distance. Meters are the basic metric units of distance and are used with standard magnitude prefixes. For example, millimeter, centimeter, decimeter, or kilometer. A meter is defined as the distance that light will travel in 1/300 millionth of a second. For navigation, we are mainly interested in the kilometre, so we will start by looking at how we can define the kilometre. A kilometre is 1,000 metres, but the speed of light definition is not very useful for navigation purposes. So let's look at a more practical definition. A kilometre is 1/10,000th of the distance from the equator to the pole. In other words, the distance from the equator to a pole is 10,000 kilometres. The circumference of the Earth is therefore 40,000 kilometres. We have seen the different units used in distance measuring and how to convert from one to another. We will now take a look at how we can calculate distances from one position to another. We now know that 1 minute of arc of latitude is equivalent to 1 nautical mile on the Earth's surface. We will start on the prime meridian. The town of Greenwich is at north 5128 and east-west 00000. We will travel north, thereby remaining on the prime meridian, all the way to the North Pole, at latitude north 9,000. We have a chelat of 38 degrees and 32 minutes. By multiplying 38 degrees by 60, we find that 38 degrees is the equivalent of 2,280 minutes. So the 38 degrees is 2,280 nautical miles. The remaining 32 minutes of chelat equates to 32 nautical miles. Therefore, 38 degrees and 32 minutes of chelat is equivalent to 2,312 nautical miles. This is the distance from Greenwich to the North Pole, directly north up the prime meridian. This is the principle used in calculating distance from chelat. The easiest way to calculate chelat, and hence distance, is to visualize the Earth split vertically along a meridian and anti-meridian. Now we will look at some more complex calculations using this principle. The Earth acts as if it were a giant magnet, creating a magnetic field around it. This field is approximately aligned with the polar axis. The magnetic field has two poles, a north and a south, although the geographic poles of the Earth are not exactly coincidental with the poles generated by the magnetic field. Additionally, the two poles of the magnetic field are not directly opposite each other. They are not antipodal. A freely suspended magnet will align itself to the Earth's magnetic field, so that the north-seeking end of the magnet will indicate the direction to the north part of the Earth's magnetic field. This phenomenon is utilized in an aircraft compass system. The north pole of the Earth's magnetic field is referred to as magnetic north. The actual geographic North Pole is some distance away from the magnetic North Pole. The magnetic North Pole is constantly moving, albeit by small amounts, of around 22 nautical miles per year. In 2005, the magnetic North Pole was close to 83 degrees of latitude, approximately 420 nautical miles from the geographic North Pole. The longitude of the magnetic North Pole was around 114 degrees west in 2005. This places the Earth's magnetic North Pole amongst the Queen Elizabeth Islands in northern Canada. This physical position is important because we need to be able to compensate for the fact that it is not coincidental with the Earth's geographic North Pole, referred to as true north. The difference between true north and magnetic north has an angular value. This angular value is referred to as variation. Variation will depend on the relative position of the observer on the Earth's surface, to magnetic north and true north. Variation can vary from 0 to a maximum of 180 degrees. Additionally, the sense of variation is important, whether magnetic north is to the east or west of true north. As the magnetic North Pole is constantly moving, variation also changes. Its numerical value is shown on most aeronautical maps. Lines that join places of equal variation are referred to as isogonals. Isogonals that indicate 0 degrees variation are also referred to as agonic lines. As we have seen, a compass will indicate the direction to magnetic north by detecting the Earth's magnetic field. The Earth's magnetic field has a vertical element as well as a horizontal element, as depicted in the diagram. The nearer to the magnetic pole, then the greater the vertical component becomes, and the less the horizontal component becomes. Eventually, at the pole, the vertical element becomes 90 degrees, due to the magnetic pole being directly below the position. The angle that the magnetic lines of force make to the horizontal is referred to as the angle of dip. This angle will be maximum at the magnetic poles and reduce as we move away from the poles. Approximately halfway between both magnetic poles, the angle of dip will be 0, as the component is all horizontal and the vertical element is nil. The position where this occurs is referred to as the magnetic equator. It is undesirable for a compass system to be influenced by the vertical element of the Earth's magnetic field, as this can induce errors. The horizontal element is used by the compass to determine magnetic north, and this is known as directive force. As can be seen in the diagram, the angle of dip will vary with increasing magnetic latitude. Example A has a low dip angle, as it is near to the magnetic equator. Example B has more dip at mid-latitudes, although the angle is acceptable. Example C has a large angle of dip, as it is near to the magnetic pole. The angle of dip is referred to as inclination, and the line of zero dip, the magnetic equator, is referred to as an aclinic line. The magnetic equator can be seen in the image on screen, together with lines of inclination over the Earth. An aircraft compass system is designed to detect the Earth's magnetic field, and as we have seen, requires the horizontal component only. The vertical component introduces errors, and one way to overcome these is to pendulously mount the detector unit. Unfortunately, there are also other influences that can diminish the compass accuracy. The compass is also sensitive to other magnetic fields. For instance, those generated by electrically driven instruments and metallic objects within the aircraft. These secondary magnetic fields can cause the compass to deviate away from magnetic north. Such distortion of the actual compass reading is referred to as deviation. Deviation can be determined for each aircraft, and this is calculated for each individual aircraft by the manufacturer and by licensed engineers periodically. If the amount of deviation is known, compensation can be made to allow for these inaccuracies. Deviation is defined as the angle measured at a point between the direction indicated by a compass needle and the direction of magnetic north. The compass actually points to compass north, as opposed to magnetic north. However, compass north is not a geographic location. It is merely magnetic north that is affected by local magnetic influences within the aircraft.
The navigation computer is used to solve navigational and flight planning calculations quickly and easily. This interactive computer-based training course produced by Oxford Aviation will teach you how to use the principal functionalities of any brand of navigational computer. In order to achieve this aim, we have created our own virtual instrument. We will begin by describing to you the construction of this virtual instrument. Actual branded instruments will vary slightly in the detail of their layout, but their main features are very similar, and their principle of operation is the same in all cases. The computer has two faces. The first face is the circular slide rule face. The circular slide rule face of the navigation computer has inner and outer scales. While the outer scale is fixed, the inner scale is free to rotate. There are two index marks on the inner scale. The red triangle with the number 10 in it is the index which is used when manipulating the computer as a rotary slide rule. We'll refer to this throughout the CBT as the 10 index. The white triangle with the 60 in it is utilized when making calculations concerning time, distance, and speed. We'll refer to this throughout the CBT as the 60 index. A cursor is provided to make the task of reading between the two scales easier and the results achieved much more accurate. To multiply one number by another, initially set the 10 index on the inner scale against the first number of the calculation on the outer scale. Next, locate the second number of the calculation on the inner scale and read off the answer opposite it on the outer scale. Remember that you'll need to make a rough estimate of the answer to establish where the decimal point will be. We'll try an example. Let's multiply 6.5 by 29. 6 multiplied by 30 equals 180, so the answer will be roughly 180. Set the 10 index on the inner scale against 6.5 on the outer scale, and read off the answer on the outer scale opposite 29 on the inner scale. The correct answer is 188.5. Note that using the cursor can sometimes help you to read the answer more precisely. To use the navigation computer as a time, speed and distance computer, we utilize the apex of the 60 index on the inner scale. If we're given a distance and a speed, we can calculate the time taken to travel that distance by setting the 60 index on the inner scale against the speed on the outer scale. Now, if we locate the distance on the outer scale, we can read off the time on the inner scale against that distance. For example, if we're travelling at 110 knots over the ground for a distance of 90 nautical miles, how long will it take us? It would be prudent for us to get an order of magnitude of the answer. The mathematically minded amongst you will probably already know that dividing distance by speed gives us time. If our ground speed is 110 nautical miles per hour, we'll require a little less than 1 hour to cover 90 nautical miles. Now let's use our navigation computer to calculate the answer. Set the 60 index against 110 on the outer scale, and, using the cursor, against 90 on the outer scale, read off the elapsed time of 49 minutes on the inner blue scale. You'll notice the inner blue scale is graduated in minutes for distance and time calculations, while the inner white scale is graduated in minutes and hours. On the inner white scale, hours are subdivided as follows: from 1 to 2 hours in 5-minute intervals, with each 10-minute interval being identified by the actual figure. From 2 to 5 hours, the subdivisions are at 10-minute intervals, with each 30 minutes being identified by the actual figure. Thereafter, hours are subdivided into unmarked 10-minute intervals. Let's now see how the inner white scale is used to calculate leg times in excess of 1 hour. For example, let's work out the duration of a flight if we have a ground speed of 95 knots and a distance of 127 nautical miles to fly. First, we'll do a rough mental calculation. If we have to travel 127 nautical miles at a ground speed of 95 nautical miles an hour, we're going to take between 1 and 2 hours to cover the distance. Now set the 60 index mark against 95 on the outer scale, and then position the cursor against 127 on the outer scale. Read off the duration of the flight, 80 minutes, or 1 hour and 20 minutes, on the inner scale. To find our speed over a given distance, first set the elapsed time on the inner scale against distance on the outer scale. Then the speed may be read off on the outer scale against the 60 index on the inner scale. Let's use an example to illustrate the method. If we've travelled a distance of 145 nautical miles in 68 minutes, what is our average ground speed for the journey? We can get a ballpark idea of the answer by saying that as our elapsed time is just more than 1 hour, our speed will be just less than 145 knots. Align 68 on the inner scale with 145 on the outer scale. Use of the cursor may help with accuracy. Using the cursor, read off our speed of 128 knots on the outer scale against the 60 index on the inner scale. To calculate the distance travelled, given an elapsed time and a known speed, place the 60 index against the speed on the outer scale. Read off the distance on the outer scale against the time on the inner scale. For example, if our ground speed is 87 knots and the time that has elapsed is 29 minutes, what's the distance that we have travelled? 29 minutes is almost half an hour, so we should travel just less than half of 87 nautical miles. Set the 60 index against 87 on the outer scale. Using the cursor, read off the distance on the outer scale against the time, 29, on the inner scale. The answer is 42 nautical miles. The computer uses the 60 index to great advantage throughout the whole of this lesson on fuel calculations. The 3 parts of this lesson will instruct you in the methods of finding the fuel required, given a consumption rate and a time, finding the fuel consumption rate, given a fuel quantity and a time, and finding the endurance, given a consumption rate and a fuel quantity. To calculate the amount of fuel required, given the rate of consumption and a known time, align the 60 index against a consumption rate per hour. Then read off the amount of fuel required on the outer scale against the time on the inner scale. An example will allow us to demonstrate the correct method. Given a rate of fuel consumption of 8.6 gallons per hour and a time of 2 hours 40 minutes, calculate the fuel required. As always, we'll get an approximate figure to allow us to judge the scale of the answer. Rounding up to 9 gallons per hour for 3 hours, we get 27 gallons, so our answer must be somewhere in that area. Align the 60 index with 86, representing 8.6 gallons an hour, on the outer scale. Now align the cursor with 2 hours and 40 minutes on the white scale, 160 minutes on the inner scale, and read off 23 from the outer scale. Our approximate figure tells us that the correct answer must be 23 gallons. To calculate a rate of fuel consumption, we set the time in minutes on the inner scale against the fuel amount, in gallons or litres, on the outer scale. The consumption rate can be read from the outer scale against the 60 index on the inner scale. We'll use an example once again to make the mode of operation clear. What's the rate of fuel consumption given that 18.4 gallons have been used during 3 hours and 20 minutes? To get a rough idea of the magnitude of the answer, mentally divide 18 by 3, which gives us somewhere in the region of 6 gallons per hour. First, align 200 minutes on the inner scale, that's 3 hours and 20 minutes, with 18.4 on the outer scale. Read off 55 on the outer scale against the 60 index on the inner scale. The mental division gave us a figure in the region of 6 gallons per hour, so 5.5 gallons per hour is the correct answer. To ascertain aircraft endurance, given a rate of consumption in either gallons or litres per hour, align the 60 index on the inner scale with the rate of consumption on the outer scale. Now align the cursor with the total fuel figure on the outer scale and read off the endurance on the inner scale. An example will enable you to see the procedure being used. What's the aircraft endurance given a total fuel of 48 gallons and a consumption rate of 8.6 gallons per hour? First, we'll get a ballpark figure. Mentally divide 48 by 8 to give us 6 hours endurance. Initially, align the 60 index on the inner scale with 86, representing the consumption of 8.6 gallons per hour on the outer scale. Now align the cursor with 48 on the outer scale. Read off the figure on the inner scale, which is 33.5. Our ballpark answer was 6 hours. Therefore, we deduce that the answer is 335 minutes, or 5 hours and 35 minutes. Note that this answer in hours and minutes can be read directly from the white scale. The function which converts nautical miles, statute miles, and kilometers utilizes the blue indices labeled naut-m and stat-m, and the red index labeled km, m, and LTR on the outer scale. An example will illustrate how the computer works. Let's convert 65 nautical miles to both statute miles and kilometers. As always, it helps enormously to get an idea of the magnitude of the answers before we start to manipulate the computer. A statute mile is a bit shorter than a nautical mile, so the answer to the first conversion will be a figure just greater than 65, while a nautical mile is almost 2 kilometers, so we'll be looking for almost 130 kilometers in that case. Initially, place 65 on the inner scale under the blue naut-m index marker on the outer scale. We would advise that full use of the cursor is necessary for accuracy of alignment in this particular exercise. Move the cursor over the stat-m index marker on the outer scale and read off 75 on the inner scale. Our rough answer puts us in the region of greater than 65, so our answer is 75 statute miles. Leaving the inner and outer scales in the same relative position, move the cursor over the red km, m, LTR index. Read off 12 under the cursor. Our rough answer led us to expect something near 130, so our answer is 120 kilometers. The indices for the function of converting meters, yards, and feet are labelled on the outer scale in blue against the words yards and feet, and red against km, m, LTR. Once again, we'll use an example to show what we mean. Convert 1500 meters into yards and feet. A meter is a bit larger than a yard, so the number of yards is going to be very similar to the number of meters. On the other hand, the number of feet in 1500 meters is going to be more than 3 times as great. First, place 15, representing the 1500 meters, on the inner scale under the km, m, LTR index on the outer scale. Moving the cursor over the yards index, read off the figure 16.4. Our approximate answer tells us that 1500 meters equals 1640 yards. Now, still maintaining the relative positions of the inner and outer scales, move the cursor over the feet index and read off 49.2. Our rough calculation tells us that the number of feet in 1500 meters is 4,920. Blue indices against kg and lb labels on the outer scale, representing kilograms and pounds, allow weight conversions to be made. To illustrate, here's an example. Convert 2,700 pounds into kilograms. To get a rough idea of the magnitude of the answer, we could use the old saw that states 2¼ pounds of jam is equal to a kilogram. Using mental arithmetic, divide 2,700 by 2 1/4. This gives us an answer in excess of 1,000 kilograms. Now set 27, representing 2,700, on the inner scale against the pound index on the outer scale, using the cursor for accuracy. Then rotate the cursor to align it with the kg index on the outer scale, and read off 12.3 from the inner scale. The order of magnitude we arrived at by using mental arithmetic indicates to us that the answer is 1,230 kilograms. Capacity conversions involve our converting between imperial gallons, US gallons, and litres. The function that enables us to convert capacity utilizes orange indices labeled imp-gal and US-gal, and the red index labeled km, m, LTR on the outer scale. Here's an example which should assist you in understanding the method used. Convert 190 imperial gallons to both US gallons and litres. In order to work out a rough conversion factor, you should bear in mind that the US gallon is slightly smaller than the imperial gallon. As a rough guide, we can say 1.9 imperial gallons equals 2 US gallons. A given quantity of fluid, therefore, will be expressed as consisting of slightly more US gallons than imperial gallons. An imperial gallon contains about 4.5 litres, and a US gallon about 3.5 litres. Rotate the inner scale so that 19, representing 190 imperial gallons, is aligned with the imp-gal index on the outer scale. Setting the cursor over the US gallons index, we can read off a figure of 22.8. Our rough calculation indicates that the answer will be 228 US gallons. Ensuring that the inner and outer scales remain in their relative positions, move the cursor until it's superimposed over the red km, m, LTR index, and read off 86.5. Our rough calculation indicates that the answer will be 865 litres. There are two blue scales on the periphery of the instrument which enable us to convert volume into weight and vice versa. They're labelled SPG, which stands for specific gravity. The first scale is used to convert pounds of fuel at various specific gravities to imperial gallons, US gallons, and litres, and vice versa. This scale can be identified by the blue letters LB adjacent to it. The other scale is used to convert kilograms of fuel at various specific gravities to imperial gallons, US gallons, and litres, and vice versa. This scale can be identified by the blue letters kg adjacent to it. An example will help you get an idea of how to use this function. Find the weight of 44 imperial gallons of aviation gasoline at a specific gravity of 0.72 in both pounds and kilograms. As usual, we have to get an estimate of the magnitude of the answers before starting to use the navigation computer. An imperial gallon of gasoline weighs 7 pounds. Therefore, 40 imperial gallons should weigh 280 pounds. Remembering from a previous example that 2 1/4 pounds is roughly equivalent to 1 kilogram, it follows that 280 pounds is going to be roughly 100 kilograms. Using the cursor, place 44 on the inner scale, under the imperial gallons index on the outer scale. Move the cursor so that it's aligned with 0.72 on the pounds SPG scale, and read off 31.7 on the inner scale. Our estimated figure tells us that the accurate answer is 317 pounds. An identical procedure, but using the US gal index instead of the imp gal index, will enable us to convert US gallons into pounds. Ensuring that the scales remain in their relative positions, move the cursor to align it with the 0.72 on the kilograms SPG scale. This is fairly straightforward if you use the graduations on the outer scale, which are exactly the same value. Read off the figure under the cursor, which is 14.4. Taking into account what our rough estimate told us, the weight of the fuel in kilograms is 144. Now for an example of how to convert a weight into a volume. As we always do, let's use an example to demonstrate how this function works. Convert 210 pounds of aviation gasoline at a specific gravity of 0.72 into imperial gallons, US gallons, and litres. We need a rough idea of the answers before we start. Every imperial gallon will weigh about 7 pounds, and 7 goes into 210 30 times, so the answer will be in the region of 30 imperial gallons. Roughly the same will apply for the US gallon. 1 litre of fuel at the same specific gravity weighs about 1.5 pounds, so 210 pounds is the approximate equivalent of 140 litres. Initially, place the cursor over the 0.72 position on the blue pounds SPG scale. Then rotate the inner scale to place 21, representing 210 pounds, under the cursor. Keeping the inner and outer scales in their same relative position, move the cursor over the orange imperial gallons index on the outer scale and read off 29.2 on the inner scale. Our rough working tells us that the answer will be exactly 29.2 imperial gallons. Once again not moving the scales, move the cursor over the orange US gal index and read off 35. This means that 210 pounds of gasoline at a specific gravity of 0.72 fills a volume of 35 US gallons. Still keeping the scales very firmly in their relative positions, move the cursor over the red km/m/LTR index on the outer scale and read off 13.25, which, according to our rough answer, means that 210 pounds of gasoline at a specific gravity of 0.72 fills a volume of 132.5 litres. The scale for temperature conversion between Fahrenheit and Celsius can be found at the bottom of the circular slide rule face. It's a simple linear comparison scale, and its use is self-evident. An explanation of 3 of the terms we're going to use would be beneficial before we investigate how to use the navigation computer in relation to altitude calculations. Height is indicated on the altimeter when its subscale is set to QFE. Height is the vertical distance above a selected ground-level datum, usually your home airfield. With QFE set, the altimeter will read 0 when the aircraft is on the ground. Altitude is indicated on the instrument when the altimeter subscale is set to QNH. Altitude is defined as the vertical distance above mean sea level. Pressure altitude is indicated on the instrument when the altimeter subscale is set to 1013.2 millibars. Pressure altitude is defined as the vertical distance above a standard pressure datum of 1013.2 millibars. You'll sometimes hear this pressure given as 1013.2 hectopascals. Pressure altitude is normally expressed as flight level, which is pressure altitude divided by 100. For instance, 4,700 feet equals flight level 47. Variations in ambient temperatures from the ICAO standard atmosphere, ISA, values cause inaccuracies in height and altitude indications on the altimeter. Thus, your indicated altitude or height will rarely, if ever, give you the true vertical separation of your aircraft from sea level or ground level. As a pilot on a local sortie with QFE set, Your true height above your airfield is of little interest, as long as the indicated height is accurate. But on cross-country flights with QNH set, you will often need to rely on your altimeter's indicated altitude to tell you your separation from a high ground beneath you. It is therefore important for pilots to be able to calculate their true altitude. Your navigation computer allows you to do this. The calculations are based on 3 parameters: indicated altitude, actual air temperature, and pressure altitude, the latter being based on ISA conditions. You'll notice that both the lesson and the test questions used indicated and pressure altitudes greater than 10,000 feet. This is because when you fly lower than that, within a temperature range typical of a temperate climate, the difference between your indicated altitude and true altitude will be minimal, provided that you have the correct value of QNH set.
The blue scale is for calculating ram rise. Theoretically, uncorrected air temperature gauges give ram air temperature, not total air temperature. However, in many aircraft, the gauge is incorrectly labelled TAT. What you see on the gauges can also be called indicated outside air temperature, or IOAT. RAT or TAT or indicated OAT is higher than the static air temperature because of kinetic and adiabatic heating. Static air temperature is sometimes called corrected outside air temperature, or COAT. OAT on its own stands for outside air temperature and is usually taken to mean static air temperature. The relationship between them is that total air temperature equals static air temperature plus ram rise. On the slide rule face of the nav computer, there is a blue scale. The outer scale is true airspeed, and the inner scale is ram rise. If the TAS is 400 knots, the ram rise is plus 17 degrees. So if, at 400 knots TAS, we have a TAT of, for example, minus 22 degrees Celsius, then the static air temperature would be minus 39 degrees Celsius.
The airspeed indicator measures dynamic pressure, not speed. When corrected for instrument error and pressure error, it gives us calibrated airspeed, or CAS. In some books and on some navigation computers, this is called rectified airspeed, or RAS. We will use the more modern and generally accepted term calibrated airspeed from now on. The relationship between true airspeed and calibrated airspeed is that CAS equals TAS multiplied by the square root of the relative density. We do not have any aircraft instrument that directly measures air density. However, you should remember that pressure, temperature and density are interrelated. If we know any 2 of them, we can find the third. We can get the pressure from the altimeter and the temperature from the air thermometer. The navigation computer converts these into the square root of the relative density and converts CAS into TAS. The airspeed indicator is calibrated to allow for compressibility at an atmospheric density of 1225 grams per cubic meter, or ISA at mean sea level. However, at any other density, which in practice means nearly always, there is compressibility error. Compressibility error is insignificant at true airspeeds up to 300 knots, but must be applied if the initial calculation gives a TAS of more than 300 knots. Let's see how we deal with it in the following example. We are at flight level 350. The static air temperature is minus 47, and the CAS is 265 knots. What is the true airspeed? Start by calculating the TAS from CAS in the usual way. In the airspeed window, set flight level 350 against -47 degrees Celsius. Find 265 knots on the inner scale. Now read off the number on the outer scale. What do you get? You should have 473 knots TAS. This is over 300. So how do we apply compressibility correction? Look at the term written under the compressibility correction window. It says TAS over 100 minus 3 divisions. So divide the initial TAS by 100 and subtract 3. This gives us 1.73 divisions. Now, in the compressibility correction window, move the index arrow 1.73 divisions to the left. It is not easy to judge this to a second decimal place, but just try to be as accurate as you sensibly can. You have moved the inner scale to the left, altering the relationship of CAS to TAS, correcting it for compressibility. Now read off the new value of TAS against 265 knots CAS on the inner scale. What do you get? You should have found a revised TAS of 457 knots. This is the final answer, and is how you correct for compressibility error. We looked at the blue scale in a previous lesson. It shows ram rise for any particular true airspeed. In this example, a true airspeed of 400 knots gives a ram rise of 17 degrees Celsius. However, when solving this problem with a temperature gauge that shows TAT, you need to know your ram rise to find the TAS. But you also need the TAS to find the ram rise. So how do we start? The way to do it is to start with the total air temperature, even though we know that it will give us a slightly wrong answer for the TAS. We then use this close but not quite accurate TAS to find a ram rise. We apply the ram rise to get a static air temperature, or SAT. We then find the TAS again, but this time using our new SAT. This time it should be correct. Let's get this clear, because it quite often causes confusion. The only reason we carry out the first calculation is to establish the static air temperature. After that, we discard it. It is the second calculation which finds the correct TAS. Let's take a worked example. The indicated air temperature, or total air temperature, is minus 28 degrees Celsius. We are at flight level 330. The CAS is 280 knots. What is the TAS? First, using the total air temperature, uncorrected for ram rise, find the approximate TAS. Set minus 28 against flight level 330 in the airspeed window. Now read off the approximate TAS on the outer scale against the CAS of 280 knots on the inner scale. What do you get? You should have 499 knots TAS. Now, although in step 1 we are calculating only an approximate TAS in order to find the ram rise, it is still worth getting it as accurate as we can. We therefore apply compressibility correction. Move the compressibility correction index 1.99 divisions, or more practically, 2 divisions to the left. What is the revised TAS? You should have found 479 knots. Now go back to the blue scale and set the cursor on 479 knots. What ram rise does this give us? You should have found an answer of 25 degrees. So if the TAT was minus 28 degrees Celsius, what is the SAT? The SAT is minus 53 degrees Celsius. We now have a static air temperature to enter with, so step 2 is simply finding TAS in the normal way and applying compressibility correction if required. Start by setting minus 53 degrees Celsius against flight level 330 in the airspeed window. Then find 280 knots CAS on the inner scale. What uncorrected TAS does this give you on the outer scale? This gives a TAS of 472 knots. Now we have to correct again for compressibility. 472 over 100 minus 3 comes to 1.72 divisions. Move the index 1.72 divisions to the left. And as before, read off the corrected TAS on the outer scale against the new position of 280 knots CAS on the inner scale. What corrected TAS do you get? You should have found a compressibility corrected TAS of 458 knots. We have now completed both step 1 and step 2 and found true airspeed starting with total air temperature.
The speed at which sound travels is referred to as Mach 1, and it's a function of temperature. Align the 10 index on the inner scale with 60 on the outer scale to expose the Mach number index in the airspeed window. In the airspeed window, align the Mach number index with the corrected temperature. To obtain the true airspeed which corresponds to a given Mach number at that temperature, align the cursor with the Mach number on the inner scale. Then read off the true airspeed which corresponds to that Mach number on the outer scale. We'll use an example to demonstrate. At Mach 0.95 with a corrected outside air temperature of minus 33 degrees Celsius, what's the true airspeed? In the airspeed window, align the Mach number index with minus 33. Align the cursor with 9.5 on the inner scale, and read off the true airspeed of 570 knots on the outer scale. Having set the Mach number index against the temperature in the airspeed window, the true airspeed may be read off on the outer scale for any given Mach number at that temperature on the inner scale, or vice versa. For example, with the scales set up as shown, what's the Mach number for a true airspeed of 510 knots? Align the cursor with 510 on the outer scale, and read off the Mach number, 0.85, on the inner scale. Similarly, for a Mach number of 0.7, true airspeed is 420 knots. We emphasize again here that the speed of sound is dependent on temperature only, and that the examples of true airspeed against Mach number just cited assume a temperature of minus 33 degrees Celsius, which is the temperature we have set against the Mach number index. All of the navigation calculations carried out on the wind face of your navigation computer are based on the triangle of velocities. Therefore, we begin our training on the use of the wind face by introducing you to the principle of the triangle of velocities. First of all, imagine a lake half a nautical mile wide. We are at position A, and we have a boat with an outboard motor which has a speed of 5 knots. In 6 minutes, we'll have travelled across to position B. Now imagine that we are standing at position A, but this time the lake has become a river with a 5-knot current. If we threw a piece of wood into the river at position A, where would it finish up in 6 minutes? Half a nautical mile downstream at position C. Now, combine these two ideas. Imagine we set off from position A, point our boat in the direction of position B, but are swept downstream by the current. Remember, both the river and our boat are travelling at 5 nautical miles per hour. That's 5 knots. We'll finish up at position B1. Let's look at the boat's path again. After 1.5 minutes, we'll be here. 1/8 of a nautical mile across the river, 1/8 of a nautical mile downstream. After 3 minutes, we're here. 1/4 of a nautical mile across and 1/4 of a nautical mile downstream. After 6 minutes, we're here. 1/2 a nautical mile across and 1/2 a nautical mile downstream. Note that when it leaves point A, the boat sets off with its bow pointing directly towards B. But because the speed and direction of the water stream is superimposed on the speed and direction of the boat, its resultant track is about 45 degrees to a line joining A and B. The triangle ABB1 represents the geometry of the situation we've just described. We can also draw a triangle based purely on directions and speeds, as we will now show. The direction of the line XY represents the direction the boat is pointing in, that is, its heading. The length of the line XY represents 5 knots. You'll appreciate that it's very important to choose a practical, convenient scale to represent speed. For instance, you need to be able to draw the triangle on a conveniently sized sheet of paper. The choice of scale is yours. It might be 1 inch equals 1 knot, 1 centimetre equals 1 knot, or whatever. The main point is that, having chosen a scale, it must be used throughout the triangle of velocities calculation. The line YZ represents the direction and speed of the river. The direction of the line XZ represents the resultant track of the boat. Its length represents its speed along that track, in this case 7 knots. Direction and speed together are known as velocity. The lines representing the individual velocities are known as vectors. An analogous situation occurs for an aircraft flying through the air, because of the effects of the wind. We can measure the effect that wind has on the track and speed of an aircraft over the ground by constructing a triangle of velocities. Let's now look at this in more detail. The first side of the triangle of velocities is called the air vector. In our analogy, it's the line the aircraft will follow if it's flying in still air conditions. The air vector has a length which corresponds to the true airspeed, and it points in the direction in which the aircraft is heading. The second side is called the wind vector. The wind vector has a length which corresponds to the wind speed, and it points in the wind direction. The line joining these two vectors is the resultant vector, the ground vector. The ground vector has a scale length which corresponds to the ground speed, and it points in the direction of the track. The angle between the air vector, the direction in which our aircraft is heading, and the ground vector, the track the aircraft follows over the ground, is known as the drift angle, or simply drift. Notice the arrowheads drawn on the vectors. One arrowhead indicates the air vector. 2 arrowheads indicates the ground vector, and 3 indicates the wind vector. Here's an example of the triangle of velocities. Suppose that our heading is 0, 0, 0 degrees true, and we had a true airspeed of 100 knots. The wind is 240 degrees at 30 knots. Don't forget it's from 240 degrees. The orientation of the line that we draw to complete the triangle of velocities gives us the track we fly over the ground, that is 012 degrees true, which shows that our drift is 12 degrees starboard. The length of that line represents our ground speed of 118 knots. Taking matters one step further, you should now easily be able to deduce that if a pilot wishes to fly due north from A to B at a true airspeed of 100 knots, with a prevailing wind from 240 degrees at 30 knots, the aircraft would have to head into wind to compensate for the drift. That situation is illustrated on your screen. The aircraft's ground speed would now be 112 knots. We must also bear in mind such matters as whether our compass directions are measured in degrees true or degrees magnetic. The usual convention is to calculate everything in degrees true and then to adjust for local magnetic variation once your calculation is finished. Always pay particular attention to this point. The wind face of the navigation computer enables us to solve triangle of velocities problems for navigational flight. The main components of this side of the computer are the rotating scale and window, the fixed drift scale, the index mark on the drift scale, the slide. The slide is two-sided. One side gives a low speed range which goes up to 230 knots, and the other a high speed range between 150 to 650 knots. There are three separate problems which can be solved on the wind face of the navigation computer. These are: given the wind and having determined our track and true airspeed, calculate the required heading and achieved ground speed. Knowing the wind, heading and true airspeed, calculate our achieved track and ground speed. Knowing our heading, true airspeed, track and ground speed, calculate the wind velocity. CPL and ATPL students need to be able to solve all three of these types of questions quickly and easily. In most problems that you solve on the wind face, you'll begin by marking the wind on the window of the rotating scale. Here's how this is done. Let's assume that we need to enter a wind from 360 degrees with a speed of 20 knots. Both these figures together give us the wind velocity, that is, its direction and speed. Set the wind direction on the rotating scale against the index mark. 360 degrees is shown on the scale as 0 degrees. Move the slide so that one of the thicker speed arcs is set under the small center circle. Speed arcs are equidistant, so it doesn't matter which arc you use. 100 has been used here. Mark the cross on the center line at a distance down from the center circle, representing a wind speed of 20 knots, that is, on the 80 knot arc. For example, set a wind velocity of 040 degrees at 25 knots. This is a wind from 040 degrees at a wind speed of 25 knots. Set 040 on the rotating scale against the index mark. Set the center circle over a thick speed arc line. Place the cross over the 75 knot speed arc. We'll now learn how to calculate the heading we must fly to make good a desired track, and the ground speed which will be achieved along that track. This is by far the most frequent navigation exercise carried out by private pilots when planning a cross-country flight. We know what track we wish to fly because we've drawn a line on our map from our airfield of departure to our destination. We'll assume that we wish to fly from Nether Hayford to Risington Harbour. We measure the track to be 240 degrees true. We elect to fly at an indicated airspeed which gives us a true airspeed of 110 knots at our chosen cruising altitude. And the wind is given as 270 degrees true at 25 knots. First of all, let's look at the triangle of velocities for this type of calculation, so that we can visualize the problem. Because we know that the wind direction we've obtained is in degrees true, we'll decide to stay with degrees true just for the moment. Our line on the map can be used as the first line of our triangle of velocities. Note, however, that the track line gives only the direction of the ground vector of our triangle of velocities. We don't yet know its length, because that will give us our ground speed. The triangle of velocities deals with directions and speeds only, not distances, so the distance between Nether Hayford and Rissington Parva is irrelevant to our calculations. Remember, we're now dealing with a vector triangle, not with lines drawn on a map. Because we know the speed and direction of the wind, we also know the direction and the length of the wind vector. As pilots, we immediately deduce that we shall have to fly heading right of track to compensate for drift. We thus draw the wind vector at the head of the ground vector, having chosen a scale for the speed, say 10 knots equals half an inch, although any suitable scale would do. All that remains for us to do now to complete the triangle of velocities is to draw in the air vector. Let's assume that we've chosen to fly at an indicated airspeed, which gives us a true airspeed of 110 knots at our chosen cruising altitude. Thus, while we don't yet know the direction of our air vector, which will give us our heading, we do know its length. Its length will be 5.5 inches, or 140 millimeters. We can set this length on a geometrical compass. Place the point of the compass at the open end of the wind vector and draw an arc intersecting the ground vector. We join this point of intersection to the open end of the wind vector to give us our air vector. We've now completed the triangle of velocities and have obtained a direction and speed for all three vectors. The wind vector, of course, we already knew. We now, though, have a direction for the air vector of 247 degrees true. This gives us the heading we must fly to achieve our desired track, as well as showing our true airspeed by its length. The ground vector now has a length from which we measure our ground speed. Or, in other words, the speed achieved along track. In our case, this is 87 knots. So our problem is solved. To make good a track of 240 degrees true, with a prevailing wind from 270 degrees true at 25 knots, an aircraft flying at a true airspeed of 110 knots will need to fly a heading of 247 degrees true, and will achieve a ground speed along track of 87 knots. Of course, as our compass or direction indicator gives us our heading relative to magnetic north, we need to adjust our calculated heading for magnetic variation in order to find the compass heading to steer. For example, if the magnetic variation were 5 degrees west, we would add 5 degrees to our calculated heading and steer 252 degrees magnetic. The angle between the ground vector and the air vector shows the amount of drift the aircraft is experiencing. In this case, 7 degrees to port. In our diagram, in order to make good its track of 240 degrees true, the aircraft has corrected for that drift by heading 7 degrees into wind, and by flying a heading of 247 degrees true. For this reason, the angle is also known as the wind correction angle. The wind face of the flight computer solves triangle velocities problems for you. We'll now show you how this is done. In this example, we plan to fly a track of 231 degrees true at a true airspeed of 100 knots with a forecast wind of 110 degrees at 20 knots. On the wind face of your navigation computer, rotate the inner scale and set the wind direction of 110 degrees against the index mark. Now adjust the slide to put a thick speed arc under the center circle. Here we've chosen the 80-knot arc, but we could have chosen any thick arc. Mark a cross on the center line of the slide, down from the center circle, at a distance representing 20 knots wind speed. In this instance, the mark must be made where the center line intersects the 60-knot position. What we've just done is to mark the length of the wind vector. Move the slide so that the arc representing our true airspeed of 100 knots is under the center circle. We set the true airspeed under the center circle because, as you'll see, the center line of the slide below the circle becomes the air vector of the triangle of velocities. Now rotate the inner scale to set the desired track of 231 degrees against the index mark. Note that the wind vector is now oriented correctly, as in the complete triangle of velocities, which you can see in the inset. The drift line of the slide, below the wind mark, now actually gives us our ground vector. When we finish the calculation, the wind mark will therefore give us our ground speed. Note that the wind mark is now nearest to the 9-degree drift line to the right of the center line, indicating that we have 9 degrees starboard drift. In this case, the computer is telling us then that we have to head 9 degrees to port to achieve our desired track. Initially, rotate the window disk to align our notional heading under the index mark. That's 231 degrees minus 9 degrees equals 222 degrees. You'll notice that the wind mark has now moved nearer to the 10-degree starboard drift line, due to the movement of the window disk. Because of this, we have to adjust the window again, to take account of this new drift of 10 degrees starboard. Rotate the window to put 221 degrees under the index. You'll see that the wind mark remains on the 10-degree drift line. The drift on the fixed scale against the track of 231 degrees is the same as the drift under the wind mark, 10 degrees. This tells us that the notional heading of 221 degrees that we've just set against the index mark is the actual heading we need to steer to achieve a track of 231 degrees. The ground speed of 108 knots can now be read off from the speed arc which passes underneath the wind mark. Again, in order to find the heading to steer on your compass, don't forget to add or subtract the local magnetic variation. Let's try another example. This time, though, we won't draw the triangle velocities onto the wind face of the computer. We'll do the calculation as you'll probably do it during your flight planning. We'll assume that we've planned a flight from Oxford to Harden via Ludlow. The wind for the whole route is given as 070 degrees true at 20 knots. Our true airspeed will be 103 knots. We need to calculate our heading and ground speed for both legs. First, we'll put the wind mark on the window. Rotate the inner scale and set the wind direction of 070 degrees against the index mark. Adjust the slide so as to put a thick speed arc under the center circle. Mark a cross on the center line of the slide, down from the center circle, at a distance representing the wind speed of 20 knots. Now adjust the slide to put the true airspeed of 103 knots under the center circle. Rotate the inner scale to set the desired track of 302 degrees against the index mark. Note that the wind mark is now over the 8-degree drift line to the left of the center line. Remember, this shows us that we're expecting port drift, so we'll have to head starboard or right to counteract that drift and achieve our desired track. Add 8 degrees to the required track, which will give you a notional heading of 310 degrees. Then move the window to put 310 degrees against the index mark. You'll notice that the wind mark has now moved onto the 9-degree drift line. Reposition the window to take account of the extra 1 degree of drift, that is, put 311 degrees against the index mark. You'll notice that the amount of drift does not change when you move the window. This amount of drift, when applied to your track, will give you the heading to fly for the required track. Read off the heading to steer of 311 degrees against the index mark. Note that our track of 302 degrees appears under the 9 degrees port drift mark on the top scale. This confirms that the drift we are applying is correct. Read off the ground speed of 114 knots from the speed arc which cuts under the wind mark. We've now calculated our heading and ground speed for the leg Oxford to Ludlow. Of course, you'll apply the local magnetic variation to find the heading to steer on your compass or direction indicator. Now we'll work out the heading and ground speed for the second leg. Leave the wind mark and the slide position as they are. Just rotate the window to put the second leg track of 349 degrees under the index. This time the wind mark moves to the 11-degree drift line to the left of the centre line. Remember, this is drift to port. Add that amount of drift to the required track, which will give you a notional heading of 360 degrees. Then move the window to put 360 degrees against the index mark. You'll notice that, though you've moved the window, the wind mark remains nearest to the 11-degree port drift line. Thus, 360 degrees is the heading we must fly to achieve the required track of 349 degrees. As a check, you can see from the drift scale that our required track of 349 degrees appears next to the 11-degree port drift line. Read off the ground speed, 98 knots, from the speed arc which cuts under the wind mark. Once again, don't forget to apply the local magnetic variation to the calculated heading to determine the course to steer on your compass or direction indicator. We've now calculated the heading and ground speed for both legs of our flight from Oxford to Harden. If, during a cross-country flight, we know the wind velocity, the true airspeed, and the heading, we can calculate the track and ground speed. Assume the wind velocity is 100 degrees at 25 knots, the heading is 130 degrees, and the true airspeed is 110 knots. We can now draw in the third side. So, if we were actually drawing the triangle of velocities to scale, we would see that the orientation of the third side was 138 degrees, giving us our track over the ground, and that its length indicated a ground speed along that track of 89 knots. The navigation computer can do this calculation for us. Set the wind. Set the heading against the index mark. Set the true airspeed under the centre circle. Read off the ground speed under the wind mark. Read off the drift to give the resulting track. If the drift is to the right of the centre line, add it to the heading. If the drift is to the left of the centre line, subtract it from the heading. We'll use an example to help explain the method. What is the track and ground speed if the wind velocity is 050 degrees at 20 knots, the heading is 170 degrees, and the true airspeed is 95 knots? Set the wind velocity 050 degrees, 20 knots. Set the heading 170 degrees against the index mark. Set the true airspeed of 95 knots under the centre circle. Read off the ground speed under the wind mark, 106 knots. Drift is 9 degrees right, so the resulting track is 179 degrees. Remember that in calculating the track, we used the wind direction and heading expressed in degrees true, because we wanted the track in degrees true, so the track line can be drawn directly on the chart. You must ensure in all your calculations using the navigation computer that your two known directions are both expressed either as degrees magnetic or degrees true. Then your answer will either be in degrees magnetic or true, as you've chosen. Never mix degrees magnetic and degrees true within a single calculation, or else your answer will be inaccurate. Imagine that you are on a cross-country flight using visual navigation methods. You're managing to keep on track, say 020 degrees, by heading left of your desired track, say 010 degrees. Your true airspeed is 90 knots. You're aware that the heading you're flying in order to stay on track is not the heading you calculated during your flight planning. You've determined that your ground speed is not as calculated. You correctly deduce that the wind is not as forecast. Therefore, you decide to use what information is at your disposal to calculate the actual wind. Let's see how you do this. First of all, we'll consider the problem using the triangle of velocities. Maintaining your true airspeed of 90 knots, you time yourself between two ground fixes and find that your ground speed is 76 knots. Let's consider the triangle of velocities more closely. We have a track direction, 0 to 0 degrees, and length, ground speed 76 knots, drawn to a suitable scale. We have heading direction, 010 degrees, and length, true airspeed 90 knots, drawn to the same scale. We can now complete the triangle of velocities by joining the two upper marks on the track and heading vectors. This gives us a wind from 330 degrees at 20 knots. The navigation computer can do this calculation for us. Put the true airspeed of 90 knots under the center circle. Align the heading of 010 degrees with the index mark. Determine whether the track is to the left or the right of the heading and by how much, by referring to the fixed scale opposite the track. In our case, the track is to the right of heading by 10 degrees. The track is therefore represented by the 10-degree drift line to the right of the center line. If the track were to the left of the heading, the wind mark would be on a drift line to the left of the center line. Place the wind mark over the 10-degree drift line where the speed arc to the value of the ground speed, 76 knots, intersects it. Rotate the window to place the wind mark on the center line down from the center circle. Read off the wind direction under the index mark, 330 degrees. The wind speed is the difference between the speed under the center circle and the speed now showing below the wind mark. 90 minus 70 equals 20. The wind velocity is 330 degrees at 20 knots. An example will make the procedure clear. The track is 280 degrees. The heading is 292 degrees. The ground speed is 110 knots, while the true airspeed is 95 knots. What is the wind velocity? Put the true airspeed of 95 knots under the center circle. Align the heading of 292 degrees with the index mark. Here, the track is to the left of the heading by 12 degrees. It's represented by the 12-degree drift line to the left of the center line. Place the wind mark over the 12-degree drift line where the speed arc to the value of the ground speed, 110 knots, intersects it. Rotate the window to place the wind mark on the center line down from the center circle. Read off the wind direction under the index mark, 050 degrees. The wind speed is the difference between the speed under the center circle and the speed now showing below the wind mark. 95 minus 69 equals 26 knots. The wind velocity is 050 degrees at 26 knots.